Okay, so hello everyone, I am SRIPAN, and today I am going to take the ninth lecture for this course Fluid Dynamics for Astrophysics under NPTEL, and I am working as an PMR fellow at ITVHU, and as per deliverables of my fellowship scheme, I am conducting this live sessions once in a week, so on Saturday 5 to 7 p.m. So this is ninth week, and there will be total 12 weeks. So after that there will be 3 more lectures coming on in upcoming weeks. So okay, so let us start with our first question. So as you see, this is a pattern like a aeroplane, right? So the following image shows V-shaped structure near the nose and tail of an aircraft moving at supersonic speeds. So you can see that this is a V-shaped structure, and also this is a V-shaped structure. Now the question is that an observer will hear a sonic boom just when the V-shaped structure passes him or her. So what does it mean by sonic boom is a pressure pulse, right, which will be felt by the observer. So now sonic boom, an observer will hear that just when the V-shaped structure passes him or her, right? It will not be heard before the pass of the V-shaped structure. Now the third thing is there will be no sonic boom. That is not a correct thing, because this is going at a supersonic speed, so it will create some shock fronts which will lead to formation of sonic booms. Now the last one is the V-shaped structure represents a shock. Obviously this is a shock because this is kind of a pressure pulse. So that means there is steep gradient of the pressure at certain point while propagating through the medium, right? So obviously this is a shock, and the observer will hear a sonic boom just when the V-shaped structure passes him or her. Okay, so just give me up to a second. So this is also A, and then this is D. Okay, so this will be answer for this question. Now let's move on to the next question. So consider the following image which shows radio emission from a supernova shell. The parts of the image that are red represents the highest intensity. The parts in yellow represent the next higher level of intensity. Parts of blue represents relatively low intensities. So choose the correct statements. Now, first of all, you need to recall how radio emission occurs. So radio emission occurs mainly due to synchrotron radiation from accelerated charged particles. Okay. Now, how much synchrotron radiation will be there? That depends upon how much charged particles are in accelerated states, right? So that depends upon the particle density also. Now the particle density in the red area should be lower in comparison to the density in the blue areas. That is not a correct thing, right? So if you have larger density, that means you are creating more synchrotron radiation. So first one cannot be a correct answer. Second one, the particle density in the red areas should be higher in comparison to the density in the blue areas, which is correct, because if the particle density is higher somewhere, that means it will create more synchrotron radiation, that means more radio emission, and that leads to your this reddish signatures in the radio map. Okay, then so B is correct. Now the roughly spherical structure is probably a shock that accelerates particles, which is again correct, because when the particles will get accelerated, then only they could emit in radio wavelengths, right? So whenever there is higher radio emission, that means there is more acceleration of charged particles, right? And now acceleration of charged particle is associated to a shock France propagation. So here you see at the center there is less radio emission, but when you go to the limb like structure, even though this is not exactly spherical, this is more or less or approximately spherical, so it gives us an indication that yes, this is a spherical structure of, and that means it is a spherical structure which is something which is accelerating the charged particles spherically asymmetric, right? So that is a signature of shock, right? Now the gas in the red areas is relatively cooler in comparison to the gas in the blue areas. We cannot predict about that, right? That does not have any consequence with this thing, right? So yeah, so it should be much hotter because it is emitting much. So for this question you should have the answer B and C. Okay, so just write that answer is B and C. Okay, so now the next question is, let's show. So consider a spherical blast which obeys the Sedov-Taylor self-similar solution. So you know about the Sedov-Taylor self-similar solutions. So pick the correct statement. Consider two time instances T1 and T2 with T2 greater than T1, right? So the energy contained in the blast wave at T2 is greater than that at T1. So energy contained in the blast wave at T2 is lesser than. So first of all, what we need to understand is what is the conditions under which the Sedov-Taylor self-similar solution exists. So one of the solution for this is there should not be any dissipation of the energy, right? So energy must remain constant. So if you look at the first three options, then you will find out that A or B, there is some greater than lesser than criteria. That means it is violating the conservation of energy, or the energy is not remaining constant, right? So the third one is the energy contained in the blast wave at T2 is equals to that at T1, right? So you have some blast wave at certain time, and then you are equating it with some with that part at some later time or some other time, right? So you are telling that both are equal. That means the energy is remaining constant from one time to the another time, right? So C is a correct answer. Now the energy contained in the blast wave oscillates up and down with time. That is not the case because energy remains constant. So next is choose the incorrect options. So this is more about some information based options. So CMA is an example of piston driven shocks. Piston driven shock situation. So this is correct, right? So CMA is an example of piston driven shock situation. So what happens is when a CME moves, CME means coronal mass ejection, which has its origin in solar corona. Solar corona is the outer atmosphere of the sun, right? So coronal mass ejection is basically a chunk of plasma which moves through the heliosphere to our earth or even beyond the earth, right? So, and it is accompanied by the solar wind. Okay, you know our solar wind from the previous lectures. So CMA is accompanied with the solar wind, and CMA is basically a chunk of plasma, right? Now you have some plasma blobs which is moving through the heliospheric region. So what happens is CMA can perturb your surroundings medium as a piston, right? And that will create some shock due to the pressure gradient formed in the localized region. So CME works as a piston to form shocks, right? So first one is correct, but you have to choose incorrect. Now in supernova explosion is due to imbalance between the inward gravitational pull and outward radiation pressure. So first of all, let us try to understand how an object like our sun, earth, how they are stable, why they are not coming to a center, because there is a energy generation mechanism going at the core of the sun. It is radiating some pressure, and obviously the sun is like a blob by the inward gravitational pull. But why this is not collapsing is there is an outward radiation pressure also, and these two things are balancing each other. Now the question is whether it will be possible for every celestial objects. Now there can be some imbalance between the inward gravitational pull and outward radiation pressure at certain age of the celestial objects, right? So if you know the main sequence stars and white dwarf, red giants, you will find out that there is an evaluation of every stars, and sun is in main sequence right now, but somehow at future it may not remain in main sequence. Rather it will go to some other places like white dwarf or red giants, right? So supernova explosion is like that. So your outward radiation pressure is not able to withstand the inward gravitational pull. That means it will collapse and the core then explodes, right? That is a supernova explosion, which is due to this imbalance between inward gravitational pull and outward radiation pressure. Okay. Now in the supernova explosion, what happens is at the core there is carbon rich or more than that. Like if you consider the white dwarf, you can find out there is a iron rich thing, right? So now in the supernova explosion, what happens? The metal elements which are at the core that those will explode in the interstellar medium. That means your interstellar medium will get metal rich. So supernova explosion is responsible for metal rich interstellar medium. Okay, so both these three things, the three options are correct. Now let us look at the fourth option. So large amount of energy deposition at localized region does not have any connection with acceleration of charged particle in that region. So shock forms when there is some pressure pulse. Now when you are giving some large amount of energy at a very localized region, right, you are depositing large amount of energy here, then it can give rise to some pressure gradient here, which in turn can generate shocks, right? So now if there is some shock formation, that can lead to the acceleration of charged particle in that region. So the last one cannot be correct, because there should be some connection between the large amount of energy deposition at localized region with the acceleration of charged particle in that region. Okay, so text box. Answer is fine. Okay. Leads to shock formation, which in turn accelerate charge particles. Okay. Fine. Yeah. Now the next one is a supernova explodes. The spherical shock waves are generated. Just give me some minutes. The supernova explodes. The spherical shock waves are generated. At time 10 seconds after explosion, the radius of the shock fronts, as measured from generation center, is 5 units. Then calculate the radius after 50 seconds. Okay. Now, when you have a spherical shock wave, which is generated due to the supernova explosions, another question is how the radius of the shock depends upon the time. So, you know, the radius of the shock depends upon the time. Like there is a formula like this: R shock R T, right? That means radius of shock at time t, that will be equals to some dimensionless variable epsilon, which is depending upon the shock, right? And then they have T square by rho 1, right? Rho 1 by 5, right? So R shock T will be proportional to e to the power 2 by 5. Okay, so there is a formula like this. Now let us look at what the question is suggesting. So R, let's say R is for earth shock, and there is a R is 1 by R is 2, that will be equals to T1 by T2 and then 2 by 5, right? So you have let's say 5 as R is 1 by, you need to know this R is 2 equals to T1 will be your 10, this will be around 5. Okay, so 2 by 5. So that means your R is 2 will be 5 into 5 to the power 2 by 5. Okay, so that will be your answer for this question. Fine. So 5 to the power 7 by 5 will be your answer. So what you can do is just take this one, right, and point out to a new slide and insert. So yeah, so I can insert it here. I think okay. Fine. So and the next question, so shock expansion velocity in case of spherical shock fronts changes with time as which one, right? So as you know that you have this shock, you know this relation, right? R, let's say shock, which is it's equals to S, right? And then E T squared by rho 1, and then this is 1 by 5, right? And then what you can do is to find out the expansion velocity, let's say Bs, right? So Bs is, just a second, so Bs, how do you going to calculate it? dRs dt, right? So take epsilon is here, E by rho 1 is the density in the ambient medium, surroundings medium, which is 1 by 5 again, and then you have t squared to the power 5, so d dt, which is t 2 by 5, right? So therefore you have some constant here. You need to know the scaling law, like, right? So Vs is this and ddt of this, so 2 by 5 t 2 by 5 minus 1, so this is a 5. Okay, so second. Okay, so therefore Vs is proportional to 2 to the power minus 3 by 5. Okay, fine. So the answer, and therefore this one is also correct answer, 2 to the power minus 3 by 5. Okay, so just take a screenshot here. Just a second. Now the next question is, okay, now till now we never consider about magnetic field. What we are considering is hydrodynamics, fluid dynamics, right? There is nothing called magnetic field in those things. Now we are entering in a regime of MHD. Okay, so now MHD means magnetohydrodynamics. You have hydrodynamics, you have magnetic field. There is a coupling between them, right? So hydrodynamics means basically you have plasma. You can have water, many things. But when you are considering MHD, that means you are considering the plasma, because it is a magnetized fluid. Okay, so first of all, I just want to point out one or two things. So what is a plasma? So basically the coarser definition is plasma is the pore state of matter which is an ionized gas, right? But every ionized gas cannot be termed as plasma. There has been one or two properties which differentiates ionized gas from a plasma. Okay, so first of all is there should be some quasi-neutrality. What does it mean by quasi-neutrality is, so you have charged particles within the plasma, right? So it is saying that you are considering a particular length scale high enough or larger enough so that the charge ensemble enclosed by that length is almost containing same amount of positive and negative charge. That will create a quasi-neutrality in that particular length scale, right? Now if you move on to smaller length scale, you will find out there is some imbalance in charge, right? So there should be a limit above which you can consider your MHD considerations, but beyond that, smaller than that length scale, you cannot consider MHD, because then there is no charge neutrality there. That is one thing. Second thing is collective behavior. So what does that mean is, you have some charge imbalance, let's say within the plasma, then the individual particles will not react differently, rather the entire collection of the particles will react in a particular manner. That is your collective behavior, right? And then when you are considering the MHD, that means you are considering a fluid. You don't consider the individual charged particles within the fluid. Okay, so first of all, the length scale has to be higher such that we can consider the quasi-neutrality. Second thing is, so you have some plasma frequency. What does it mean by plasma frequency is, if you create some charge imbalance within the plasma, then what happens is, you have some scattering assault. So you have created the charge imbalance by some displacement of charge particle from its initial position. So that will create an electric field, right? So now what happens, that that electric field will try to help the charge particle to get its original position back, but then it has some inertia associated with it, right? So it will go in this different the other side, and then again the electric field changes its direction, and then again it tries to get back the charged particle to its original position, and then inertia again. So this is a cyclic kind of a process. So that is your plasma frequency. Now when you are considering this, you are considering a collective behavior, right? You are not considering a particular particle. Now when you have the individual particles in your microscopic scale, that will also have some frequency associated to it, which is the ion gyration frequency. Okay, so this frequency should be much. So what happens, the length scale has to be higher, so frequency has to be lower. Okay, so if you look at the options right now, so MHD is applicable for length scales that are much smaller than the charge separation length scale, which is not correct. MHD is applicable for length scales that are much larger than the charge separation length scale. B is correct. MHD is applicable for frequencies that are much lower than the plasma frequency, which is correct because the temporal scale has to be higher. So MHD is applicable for frequencies that are much higher than the plasma frequency, which is not obviously correct. So if we look at the options, I will have next box. Answer is and then C. Okay. Fine. Now the next question is, so consider the MHD induction equation. So if you look at this induction equation, you will have a feel that your magnetic field and how the magnetic field is going to change with time, it depends upon two terms. First one is curl of V cross B, which is magnetic advection term, and it tells that magnetic flux should remain conserved as the magnetic field is changing with the time, right? So that means del B del T equals to curl of V cos B. It basically gives you that the change in the magnetic field with the time depends upon the magnetic flux, right? That is the magnetic flux conservation theorem. Now the other term in the right hand side is eta grad square B. So you see here, eta is a magnetic diffusivity, and if you just forget the first term on right hand side, you will find out that this is a diffusion equation, right? So when you have just del B del T equals to curl cross B cross B, it gives you an impression that if plasma is moving at a certain speed, then magnetic field will also move with that plasma, also be dragged with the plasma, so that the magnetic flux embedded in the plasma should remain conserved during this motion. That is the first term's contribution. Now the second term is saying that if there is grad square B is quite high, and the eta is quite high, there is two options: either eta is very high, grad square b is non-zero. Second one is eta it's not that much high, but grad square b is quite high. Now grad square b is quite high, what does that mean is, so let's say you have two magnetic field lines in which your magnetic field vector is going in opposite directions. So for smaller length scale you have plus b and minus b. There is a strip gradient in the grad square b, right? So grad square b will be large. So in that case there will be that magnetic diffusion, fine, from one side to another side. So how a diffusion occurs is, if you have some gradient in between two sides in a particular medium or particular ensemble, so from high pressure to low pressure there will be a flow of those quantity which is in imbalanced state. Now here you have grad square b, so there should be some flow. Now in that case, now magnetic field is going, but whether plasma is going. So that is now the case here, right? Because only now this flux freezing condition, that is the flux is remaining constant, is violated in that particular localized region where your grad square b is very much very much high. Okay, now with all this knowledge, let us look at the options. First term on right hand side of the equation covers the decay of b, that is exactly not. Okay, the second term on the right hand side of the equation covers the decay of b, that is correct. Okay, so and then the first term on the right hand side of the equation is important, and low magnetic Reynolds number. Now till now you guys know about Reynolds number, right? Now here it is calling you magnetic Reynolds number. How do you calculate magnetic Reynolds number? Is you have R M, right, and it's basically the ratio of these two terms, that means VB by L, right, VB by L, and then divided by this, right? So if you just divide by this is eta B L square. Okay, so that means you have what? V L by eta. Okay, this is your Rn, right? So now the first term on the right hand side of the equation is important, and low magnetic Reynolds number. Now if this is this, so that means this is like this. So if the PL is less than equals to eta, right? So if this is the case, so that means the first term will be negligible for low magnetic Reynolds number. And now the last is the first term on the right hand side of the equation is important, a high magnetic Reynolds number. Now if it is this Bn greater than eta, that will lead to high magnetic Reynolds number, and that will be the case when the first term on the right hand side of the equation is important. Okay, so if you try to answer it here, so answer is B and D. Okay, fine. So that's the case. It's very disappointing that at in every classes there are no students who are attending the class, and Yeah, so I have this much content which are relatable to the lectures happened in week 9. So, so I will stop here today because I think the every topics that have been taught in the class are covered through this objective type questions. I hope this will be helpful for the students who are really keen to have some knowledge about the hydrodynamics and MHD. And I'm very disappointed with that fact that there is no students who are attending the classes, and still I have to talk to myself for the entire lecture sessions. So, but it's okay. I think it's not in my hand, so it's fine. Let's meet on next Saturday. Thank you very much.